I'm happy to be here. I'm an amateur astronomer as well as a physicist. I don't do astronomy for my professional work, but I like to get out with my telescope. And as I was saying when we were chatting just a few minutes ago, it's been extraordinarily warm here. So I've been out a couple nights this week. In January, I don't often get out. A year ago this time, it was minus 40 degrees Celsius, which is also minus 40 degrees Fahrenheit. So I said I'm a bit of a wimp. I don't go out with my scope in those temperatures. By training, I'm a relativist. It's kind of interesting that I got a job as a senior lab instructor, but by training, I'm a relativist. So today I'm going to talk about gravitational wave astronomy, and it's going to be descriptive and non-mathematical, but I have not written down any equations in my slides, but I think I might talk about one equation. We'll see. Okay. If we have two compact objects orbiting each other, it could be two black holes or two neutron stars, or a black hole and a neutron star, they produce gravitational waves. Well, it's actually true that any two objects that orbit each other produce gravitational waves. So gravitational waves are being produced as the moon orbits the Earth and as the sun orbits, as the Earth orbits the sun, but they're extremely weak, and I can't see them being detected in the next few centuries. So in order to produce gravitational waves that we can detect, we need strong sources, and that's why we need these compact objects in tight orbits. So black holes and neutron stars are produced when massive enough stars end their lives in a supernova explosion. And two of the outcomes are black holes and neutron stars. Neutron stars are when you get all the electrons in an atom compressed into the nucleus, and they join with the protons to form neutrons. So we finally saw this in 2015 using incredibly sensitive apparatus. You will be amazed at how sensitive this apparatus is when I get to it partway through the lecture. So we first saw them in 2015. It took decades of work on the experimental apparatus to get the apparatus sensitive enough to make the detection. It took decades of work to make the theoretical predictions that we could compare to the experimental apparatus. And I'll comment a little bit more about this again in a few slides. So the first detection was made in 2015, and immediately, as soon as possible, a Nobel Prize was awarded. So sometimes it takes decades to award Nobel Prizes for major works in science. Part of the reason is that if you do a good work in theoretical, say, physics, you need experimental verification in order to get your prize for theoretical physics. So if you come up with a great piece of theory, but no one can come up with an experiment to test your theory, you're never going to get the Nobel Prize. So immediately there was a Nobel Prize awarded to Weiss, Thorne, and Barish. Weiss is an interesting character. He dropped out of university, and I've given a link to his story. So he dropped out of university to follow a romantic interest. And when the romantic interest didn't work out, he tried to get back into university, and they said, no, you flunked out. But eventually, a few years later, he was able to get back into university and finish his PhD, and end up being a first-class physicist who wins a Nobel Prize, as well as being a university dropout. Okay. How do we know what makes up the stuff out there? What's the stuff out there composed of? What's the sun composed of? The planets of the atmosphere, the atmospheres of the planets, the other stars. You know, is the moon made of cheese? How do we know what the stuff is made of? Well, you can say, well, we've brought back moon rocks. I mean, the last time we walked on the moon was almost 50 years ago. I believe it was 1972. So as long as you're not one of these conspiracy theorists who believes that the Apollo astronauts did not walk on the moon, we do have moon rocks, but you know, we've never brought back stuff, say, from Jupiter, let alone other stars. So how do we know what they're made of? Well, we use electromagnetic radiation waves to give us much knowledge, and for us here at SGL, much pleasure. We take a lot of pleasure in, I'm not an imager, but many of you guys are imagers who make fantastic images, and you get a lot of pleasure from doing that. I get a lot of pleasure from just going out with my scope and being at the eyepiece. But it also gives us quantitative knowledge for science. So before I get into the gravitational wave stuff, I'll first talk about electromagnetic waves for a bit. So electromagnetic radiation. So sometimes when a scientist, a physicist says light waves or light radiation, they mean the full spectrum, including stuff that we can't see, like, whoops, I didn't mean to do that, like gamma rays, X-rays, and microwave, and radio waves, and so on. The visible spectrum only makes up a little part of the electromagnetic spectrum. So we blow up the visible spectrum below. And we use the spectrum for astronomy to get all kinds of useful information. So for example, we've radar ranged Venus. We've bounced radar signals off Venus and timed how long they take to come back. And by doing this, we get the distance of Venus because we know the radar is moving at the speed of light. So if we time how long it takes to go there and back and we know the speed, we get the distance. We know the composition of astronomical objects via spectroscopy, which some folks here at SGL do, and there's a forum here for that. What predicts these spectral patterns is quantum theory. Well, we're not going to get into quantum theory, but instead of having that full rainbow of colors that I had on the previous slide, particular elements only give off very specific colors. And for light, different colors correspond to different wavelengths. Just like for sound, different pitches correspond to different wavelengths. So for specific elements, we have specific colors, very specific colors that are given off. So that we know that if we see one of these patterns in light that we receive from out there, we can say, aha, there's helium. There it is. And guess what? Helium was discovered out there before it was discovered on the Earth. It was discovered on the sun, Helios. It was discovered on the sun, I believe, before we found the spectrum here on the Earth. But anyways, now we can match up. These are really fingerprints of what stuff is made of, these different patterns. And I've given 4 examples here: sodium, helium, neon, and mercury. And I teach labs at my university as well as lectures. And in second-year labs, we have a spectroscope, and we do these elements. We do all of these elements in a lab I teach at my university. So by seeing these fingerprints, these different patterns of light, in the light we get from way out there, we can figure out what the stuff way out there is made of. And we can do more than that. Something called the Doppler shift shifts wavelengths when something that's emitting a wave is moving with respect to something that's receiving that wave. So if you stand by the side of the road and you watch cars go by, that's a Doppler shift. The sound is higher in pitch as the car is approaching you, and lower in pitch after it gets by you and is receding from you. So the wavelength changes. It's shorter for something moving towards you and longer for something moving away from you. And the same is true for light. Well, I just said wavelengths corresponds to colors, so things get shifted. And in particular, things that are moving away from us get shifted towards the red end of the spectrum. So that these two patterns of light, and in this case, we're missing certain colors, and they're indicated as black lines where we're missing certain specific colors. It's the same pattern in the top and in the bottom, but the pattern has been shifted towards the red end of the spectrum. And by measuring the exact amount of that shift, we get out a speed between what's emitting the object and us receiving the object is the speed. So what produces electromagnetic radiation? Accelerating electric charges, electrons. So if you're using your mobile phone and you're transmitting to a cell tower or something, what your phone is doing is taking your voice and converting it to electricity and using that electricity to accelerate electrons back and forth in your phone, which produces a signal. Conversely, if you're receiving a signal with your phone, the waves, the electromagnetic waves pass through your phone, and when they do that, a voltage is produced in your phone that accelerate, or the waves accelerate electrons back and forth in your phone, which is produced which is turned into a voltage that you can hear in your ear when your friend is speaking. So accelerating charges both produce the electromagnetic radiation and are what's used to detect the electromagnetic radiation. Now I want to flip this over to gravitational radiation. So first, a little bit about gravity. Newton came up with the first quantitative theory of gravity. Action at a distance, there's immediate action. There's a force between any two objects that have mass, like the sun and the earth. And that was, almost 350 years ago. Einstein modified this greatly at the end of 1915, and he produced a theory of gravity that says gravity is a curvature of space-time. Now, Einstein's theory of gravity works everywhere that Newton's theory of gravity works, and it works in other places. Like, for example, explaining precisely the orbit of Mercury around the sun. Newton's theory of gravity can't do that. So Newton's theory of gravity works well in a lot of places. If I drop my keys to the floor, I can calculate what's happening using Newton's theory of gravity. I could also calculate what's happening using Einstein's curved theory of space-time when I drop my keys to the floor, but that would be insane. Just use Newton's theory of gravity for that. And I've included a picture of Einstein. You've probably all seen pictures of Einstein, but many of you might not have seen Einstein as he looks here. You would have seen him as an older man. This is what he looked like when he did his science. So I talked about electromagnetic radiation, and I said that accelerating electrons, electric charges, produce electromagnetic radiation. Well, something similar is true for gravitational radiation, accelerating gravitational charges. Don't worry, you all know what gravitational charges are, they're just masses. So accelerating gravitational charges, whoops, Control C without changing a word that I was supposed to change. So the top bullet point should read, accelerating gravitational charges, masses, produce gravitational waves. I did a Control C on one of my previous slides and forgot to change the relative words. I'm sure many of you have done something similar. So that's gravitational waves in the top slide, in the top point. Similarly, gravitational waves are detected by the accelerations that they produce in masses. And these gravitational waves were first predicted by Einstein shortly after he came up with his theory of gravity in 1916. Also in 1918, Einstein was human. His first paper on gravitational waves had a mistake in it. He corrected this mistake in 1918. So Einstein was human, he made mistakes. His first paper on gravitational waves had a mistake in it, which he had to correct. Now, anything that's orbiting, again, like the moon around the Earth around the sun, anything that's orbiting is accelerating because it's changing direction. And since it's accelerating, and I said accelerating masses produce gravitational waves, all these orbiting things produce gravitational waves. But the effect these gravitational waves have is very small. So we need something like large masses in tight orbits to produce waves that we can actually detect. So we need stuff like black holes orbiting black holes, neutron stars orbiting black holes, or neutron stars orbiting neutron stars in tight orbits. We need this in order to have a chance of detecting these gravitational waves. So let's see if this works. So here are two generic objects orbiting, and here's a little video of the gravitational waves being produced as they orbit, or and gravitational waves. Since gravity is curvature of space-time, gravitational waves are ripples in space-time. And here they are propagating out from the two orbiting objects. Notice how they're propagating out. They propagate out at the speed of light. So two black holes, any two objects orbiting each other will produce this. The Earth orbiting the sun, but let's suppose we have a couple of black holes orbiting here. Okay, so we produce these gravitational waves. What effect do they have? Well, let's suppose out in space we had a circle of test masses. As these ripples pass through this circle of test masses, they induce this motion in the test masses. You know, it's circular in the middle, and then it's elliptical, along the horizontal axis and then the vertical axis. So it produces this very strange effect, but it's this effect that allows us to detect gravitational waves. So as the ripples that you saw in the previous slide propagate out, they would do this to a circle of test masses out in space. These are just hypothetical masses out in space. And we're going to use this effect to detect gravitational waves. And here we have it, a simplified version of what's used to detect gravitational waves. Now, I'll try not to click. I clicked. Okay, can you see my mouse pointer?
Yes, we can. Yeah.
So here's a laser that's fired at a partial mirror. So part of the laser beam was reflected by the mirror, goes up, and part goes across. And then this is called an arm. It goes up this arm and is reflected by a mirror and goes through the partial mirror and is received. So that's one path. Off the mirror, up, back down, through the mirror, and received. The other path that I want to consider is through the partial mirror, reflected off a mirror, and back, reflected by the partial mirror and received. So we've got two light signals being received, the one that goes up and down, the one that goes across and back and then down. We've got two light signals that are being received. And when these two signals are combined at the bottom, they produce an interference pattern. So again, this is something I teach in a second-year university lab. One of these, this is called an interferometer. Each arm in the interferometer I use for students, probably about 8 inches long or 20 centimeters. The ones that are used to detect gravitational waves are 4 kilometers long. These are 4 kilometers long vacuum chambers. I don't know if they still are, but when they were first constructed, they were the largest vacuum chambers ever constructed. So they're 4 kilometers long. So we combine the two signals and we get a pattern. If we change the length of one of the arms just slightly, we'll see a shift in the pattern that we get. Doesn't matter which arm you choose. If you change the length, you'll see a shift in the pattern. So the pattern you see depends on the relative lengths of the two arms. And the actual setup is more sophisticated. They actually bounce the light back and forth, I think, several hundred times in each arm before receiving it. Again, it's because 4 kilometers is not long enough to be sensitive enough to detect gravitational waves. So this is done underground, and we've sort of gotten a top view. Imagine a drone high above the Earth looking down and with X-ray vision so you could see under the Earth. These arms are under the Earth and they're parallel to the surface of the Earth. So this is what we use to detect the gravitational wave radiation. Now remember what the visual I had for what happens to a circle of masses. And this effect happens to the Earth as the gravitational waves go through the Earth. It's stretched a little bit in one direction. It goes back to being a circle. It's stretched a little bit in the other direction and repeats. So when nothing's being stretched, the interferometer is like it normally is. But as the waves pass through, first this arm will be expanded and this arm will be compressed. Then they'll both be the same length. And then the other arm will be expanded and this arm will be compressed. And this will repeat over and over again. And you'll see a shifting pattern back and forth as the gravitational wave goes through this amazing set of apparatus. So these arm lengths actually change in length as the gravitational wave goes through. How much do the arm lengths change? The arm lengths are 4 kilometers long. How much do the arm lengths change? A centimeter, a millimeter, a micron? Well, a micron is way too large. Okay, and before I get exactly how much each arm changes, let's see what happens. So in the previous slide, we saw that the gravitational waves propagating out from 2 objects that were orbiting each other. These gravitational waves carry away energy from the orbits. They carry away energy from the orbits as they propagate out, and the orbits become tighter. The objects spiral in, and they eventually merge. So here's about a minute video produced, I believe, with a supercomputer. This is an actual video. This is not a cartoon animation. This is an actual video of what state-of-the-art theory predicts. I believe produced using a supercomputer. So this will take a minute or so. So the 2 black holes are orbiting each other. And it's hard to notice, but they're spiraling in towards each other, and they will eventually merge. Here they go. And after they merge, it takes them a little while to settle down. So eventually the 2 objects merge, and then the merged object rings like a bell for a little bit, like a damped bell. Rings like a bell for a little bit after the merger. Why am I not going forward? Here we go. So here's what the video showed. I keep hitting my screen accidentally. You know, the 2 objects are in a spiraling orbit. As they spiral in towards each other, the gravitational radiation becomes stronger. Here's a picture of the gravitational radiation in the red. So it's becoming bigger and bigger and bigger. Eventually they start merging. That's when you get the most gravitational radiation released. And then the merged object rings like a bell for a while. So in order to match theory and experiment, first you have to make an experimental, well, not first, but you have to do two things. You have to make an experimental detection. You have to be able to detect something, and you have to have a theoretical prediction to which you can compare the theoretical detection. So the theoretical prediction was calculated in this region, the spiraling orbit, and in this region, the ring down, when you've got a merged object ringing. Both of these theoretical calculations were done, some of them over half a century ago, some of them around half a century ago, 50 years ago. But the part where the objects are merging, when the black holes are merging, that was a very difficult calculation, and it was done in 2005. So one of the Nobel Prize winners was Kip Thorne, and I was a postgraduate student in 1992, and I happened to go to a conference where Thorne was presenting on the state of the art, what was going on in 1992. So he was talking about how the apparatus was gradually getting more sensitive, and how the theoretical people were working on how to do this merger calculation, but the apparatus was nowhere near sensitive enough. And the theory guys were way far away from being able to do a calculation. So I was at a talk that Thorne gave, and he said at this talk, and I'll always remember this, he sort of said, you know, who's going to win first? Who's going to get results first? It's a competition. Will the experimental apparatus become sensitive enough to detect waves, gravitational waves, before the theory people have finished their calculation? Well, it worked out the other way around. The theory people did the calculation. It took them 13 years from the time he said this in 2005. And to do the calculation required new supercomputers and brand new numerical techniques that ran on these supercomputers. So the theoretical prediction was made in 2005, and the detection was made 10 years later, experimentally, in 2015. So here is the first detection in 2015. So keep in mind this signal, theoretical prediction. Well, of course, in practice, we'll have a noisy signal. And I think we're all familiar with noise in our signals. So, but look how closely that follows the theoretical prediction, especially when you clean up the noise. So it was made, there were two detectors online, one in the state of Washington and one in the state of Louisiana. They both detected the signal. So they really wanted two detectors to detect the signal because they're working with such finicky and sensitive apparatus that, you know, they wanted to make sure that the signal they saw was real and not spurious. It wasn't somebody driving a car in the car park above the detector. It was a real gravitational wave. So they both detected the wave, and the cleaned up signal looked just like the theoretical prediction. Amazing. So this was two black holes merging in a galaxy far, far away, billions of light years away. So gravitational wave observatories are located in the states of Washington and Louisiana. There's another one in Italy, and there's one that's almost online, probably within 5 years. One will be online in India. And it's important to have gravitational detectors on different parts of the Earth, because that will give us better directional information on where the source of the gravitational waves is, and gives us better information on maybe something optically happened there at the same time. Maybe we'll get a correspondence between a gravitational wave signal and an optical signal. In order to do that, we should have some, be able to make a directional call on the signal. Okay, so before I get back to the gravitational wave stuff, first a little bit about science. I can't remember whether I ever posted this to SGL or not. but I like this statement. Science progresses one funeral at a time. It's a paraphrase of Max Planck, who made a longer statement. But what does that mean? Well, as the decades roll on, we tend to come up with new theories. The theory of relativity was a better theory of gravity than Newton's theory. But when we get these new theory, the old guard of physicists or of scientists tend not to accept the new theory. No matter how much evidence there is for the new theory, there'll be a bunch of the older people, the older physicists, who say, oh yeah, but tomorrow we're going to measure something that will overturn all this and we'll be back to something more intuitive. It never seems to happen that way. So how does a new theory become accepted? When the old guard of physicists dies off. So science progresses one funeral at a time. Science doesn't prove anything. We never prove anything. In order to prove that a theory of gravity is correct, we'd have to make measurements in all possible situations. So we can't do that. So we can get lots of evidence and we gain confidence as we get experimental evidence for our theories, but we can never prove that the theory is true. So what we do is come up with a theoretical model, and we make predictions using this model, and then we go out, we do experiments and make observations to try and test these predictions. And I like the way Steven Weinberg, another Nobel Prize winner in physics, puts it. He's possibly the greatest living physicist. Scientific research is more honestly reported as a tangle of deduction, induction, and guesswork. Well, let's try this. Let's see if this works. There's the guess. The induction, we make some observations, and from those observations, we induce or guess at a model. And once we have our model, then we use our model using logic or deduction to make further predictions that we try and go out and test. So I think Steven Weinberg phrased it very well. So we have theoretical models of black holes. And when we do calculations with these models of black holes, when black holes merge, we come up with theoretical predictions for gravitational waveforms, particular shapes for these waveforms. And these shapes, these exact shapes have been observed. So this is the most direct evidence yet for black holes. Nobody has come up with a competing theory that doesn't involve black holes that explains the gravitational waveforms that we have seen. The only theory that currently predicts these waveforms are our theories of black holes. This is very strong evidence for the existence of black holes. So that's the biggest piece of information that we've gotten from gravitational wave astronomy. We've also, from these waveforms, extracted the masses, the particular masses of the black holes involved. And we've gotten some surprises. So there was a signal that was received in 2019 that seemed to indicate that two black holes merged, and the black holes had masses of 66 and 85 solar masses. 66 and 85 times the mass of the sun, with the masses of the black holes. And we don't know how to form black holes that have these masses. So we know how to form supermassive black holes, like at the center of our galaxy. Two people who won the latest Nobel Prize in physics were awarded the Nobel Prize for studying the black hole at the center of our galaxy, which has a mass of about 4 million solar masses. So we know how to produce them. We know how to produce smaller black holes that happen when large stars go supernova at the end of their lives. But this is a little larger than we think can be produced, or than we thought could be produced by supernova at the end of a large star's life. But that seems to be the only explanation. Anyways, the theorists have now gone back to the drawing board and are now trying to come up with models that predict the end results of supernovas that can have these masses. I think it was 2 days ago, I got my latest issue of Astronomy magazine, and there was a small half-page report on this story, these intermediate mass black holes. Intermediate mass, so between the masses of what we thought could be produced by supernova and the masses that are produced in the centers of galaxies when a bunch of stuff merges together. A very exciting piece of information that we can extract is a new way to measure cosmological distances. But in order to do this, we have to have an optical counterpart for the gravity wave that we detect. So the gravitational waves will come from some event way out there. Well, hopefully that event also produces light waves that we can see. And if we can match up the gravity waves to the light waves and measure the redshift, about which I talked earlier, of the light waves, then we could come up with a completely new way to measure distances, completely new. And this will have cosmological applications. It could strengthen the case for dark energy, could weaken the case for dark energy. Most people think it will strengthen the case for dark energy when we do this. There's something called the Hubble parameter, which is sort of a measure of the rate of expansion of the universe. And right now we have two different ways of measuring this, and they're giving slightly different results. But the results are sufficiently different that it's a bit of a puzzle. Well, this may give us a new way if we can find enough events that from which we can see light and gravitational waves. If we can find enough, we might be able to get a more precise measurement of these expansion of the universe and maybe get rid of the controversy that now exists. Okay, where's my mouse? The future? Well, we have these large interferometers below the surface of the Earth that shine light waves or laser light along arms that are 4 kilometers long. People would like to do this in space, produce light sources in space that orbit the sun and produce 3 of them. We're close to one of them here. Here's the Earth orbiting the sun. And here's some event way off in the distance. The scale has been altered. If the scale between the sun and the Earth is this is not the scale to the distant event. So way off in the distance, we have black holes merging, or actually supermassive black holes merging. Like at the centers of galaxies, where there are supermassive black holes, we may actually have supermassive black holes merging. That will produce gravitational radiation that cannot be detected by the detectors that we currently have, because the radiation has wavelength that's too long. So just like we use radio telescopes to detect longer wavelength electromagnetic radiation as compared to optical telescopes, we need different types of telescopes, gravitational wave telescopes or antenna, to receive different wavelengths of gravitational waves. So this will really work well for supermassive black hole mergers in the centers of galaxies. So the length of an arm here is 2.5 million kilometers. And did I forget to talk about it? I think it was a bullet point, but I must have forgotten to talk about it. The length in the gravitational wave detectors that we're using now under the Earth that have 4 kilometer long arms, how much did the arm change? How much did the arm length change? 1/1000,000,000 of a meter. So take a meter split it up into a billion equal parts, take one of those parts, split that up into a billion equal parts, and that's how much an arm length changed over a distance of 4 kilometers. And we were able to measure that. That distance is at 1,000th of the diameter of a hydrogen nucleus. That's what we measured. It took decades to build up the sensitivity to where we could do this. So we hope to put satellites in space to measure longer wavelength gravitational waves. A tentative timetable is 15 years, but we all know how projects tend to get pushed off into the future. So I would be pretty amazed if it happens in 15 years. I'd be quite glad if it happens in 15 years. But anyways, it's something to look forward to. At least I hope I can look forward to this. So thanks for sitting through this. That's all, folks.
George, thank you very much. That was I was just writing a question down there, so I didn't forget, and I'll come to that.
You'll now probably forget.
No, that's why I've written it down, because I am used. Well, actually, I was just looking at the chat. I don't think anybody's actually got a question at this precise moment in time, so I'm going to jump in first. So, George, just on that last point, then, if the earthbound one is measuring distances, as you say, of a billionth of a meter, what sort of distances are the spacebound ones going to be measuring? How accurate are they going to be?
Yes, I do not know. Now, there may be technical information out there. I don't know that one. So sorry, but I may be able to come back with an answer on that. So I'll elaborate just a little bit. They've done a sort of a mini mission of this. They have put up some interferometers in space with short arm lengths. And what did they measure on this mini mission? Again, they're just testing the apparatus. They're not expecting to detect gravitational waves. They just put up one arm, and you need multiple arms to get the interference. They put up one arm, and I believe they detected 100th of a nanometer. So what's a nanometer? A nanometer is a billionth of a meter. 100th of a nanometer they've done in space right now. So I don't know. I suspect it wouldn't have to be such a small distance, changing distance that we would measure.
Gosh, somebody's put on there is mind blowing. It is. It's phenomenal. My tiny brain can't cope with a billion, let alone a billionth of a billionth. That's phenomenal.
Andy asked during the talk, and he's just asked again now, what was the time scale in the wave graph? You know, the actual the graph produced by the vectors.
I cut that out. Was that in the talk? Did I include that or not? No. Shoot. So I'm probably not going to be able to answer many of the technical questions. But I think you're looking at a fraction of a second. Seconds at most.
Gosh, okay.
But not some minute fraction of a second. You know, I think you're looking at, roughly on the time scale of a second.
Okay.
Okay. Norman has a question. Norman, if you want to, good evening, sir. How are you? If you want to unmute yourself.
Oh, let me press the button.
Oh, Grant has not pressed the button. There we go. Try again.
Yeah. Gravitational waves, are they subject to the same laws that would predict entanglement?
Wow. The gravitational waves are macroscopic objects, just like the light waves are. So when we do entanglement with light, we do it almost on the individual photon level. So we don't do the entanglement with continuous light waves, like lasers or whatever. We do it almost on the photon, level. So we have yet to come up with a theory of gravitons.
Ah, right. That
It does
would,
not exist.
yeah.
I mean, someone does that and it's verified, they should win 100 Nobel Prizes.
Right. Thank you. Yeah, it was the duality wave particle.
Right.
Yeah.
But that's almost waves and probability. So it's so there very much is a wave-particle duality, but that's predicted by quantum theory. And as I say, one of the great unsolved questions in physics is a quantum theory of gravity. And a technical reason is that gravity is nonlinear. It doesn't add like light. Light, you just add the stuff up, one source at a time. You just add them, but you can't do that with gravity. So, you know, I like to say to my students, we'll probably have a quantum theory of gravity sometime in the next 200 years.
Thank you.
Excellent. Thank you. Alien, good evening, sir. How are you? Do you want to ask your question?
He hasn't got a mic, I don't think.
Yes.
Or has he?
Has he? Yeah, he does normally.
He was just gesticulating. Oh, there we go.
Okay, I'm on the mic. The question was, I noticed the detectors on Earth and the ones in space were two-dimensional. Is gravity waves a three-dimensional effect, or just
Sure,
two-dimensional?
it's three-dimensional.
It's three-dimensional.
I'll go one step further. I'll say it's four-dimensional
Okay.
with time, but there's 3 dimensions in space, yes.
So why only we measure in two?
Because 2 is sufficient. It's sufficient to measure the change in length along 2 to compare to a prediction.
Okay. Okay.
Good stuff. Excellent. Thanks, Alien. Thanks for the question.
I think Martin was next.
Martin B. Good evening, Mr. B. How are we?
Unmute yourself, shall I?
Yeah, unmute yourself.
Okay, well, it's just a very simple question. I remember the first gravitational waves being detected, and it's very exciting, but work's obviously carrying on. I just wondered the frequency with which these interferometers are detecting gravitational waves. Are they rare events, or are they happening all the time?
We're getting several a year now, I think. So is that all the time? I'm not sure. But we've accumulated quite a few events now. And the physicists themselves have not remained static in the just over 5 years that we've been detecting gravitational waves. They have improved the sensitivity of the equipment. So by improving the sensitivity, we can now see further out into space. So there are gravitational waves events that are happening that are too far away, so that the signal is so weak when it gets here, we don't detect it. But by increasing the sensitivity, we increase the volume of space for which we can see gravitational wave sources. So we're always increasing the sensitivity, and they've increased it substantially, I think, since 2015. But we are, I think, detecting a few a year.
And is it changing our thinking, George? I mean, are we getting any surprises? Things behaving in a way that is not expected?
Well, we've only had a minor surprise, and that was these intermediate massive black holes. And it's interesting that you say this. Darn, I'm not going to be able to pull up the book quickly enough. But Kip Thorne, one of the people who won the Nobel Prize, wrote a semi-popular level book in 1996. So long before 96, in the 90s. No, I don't know if it's 96, in the 90s. And, you know, he was talking about this. You know, are there going to be any surprises? He thought there were. He thought that there would be a discrepancy between our theoretical calculations and what we actually measure. But so far, it's been dead on. Darn. All physicists want surprises.
Well, thank you, George.
Thanks, Martin. Andy's got another question. Andy, have you got a microphone? You're quite welcome to unmute yourself and ask that one.
I think I have. Can you hear me?
We can. Yeah.
Yeah, so I mean, as an engineer, I'm kind of interested in how they refined the sort of noise resistance and the sensitivity of this thing, because you know the walls of my house are moving apart over the course of years by whole millimeters. So, you know, for example, how do you stop a 4 kilometer long detector from doing that?
Yeah, I do not know technical details. Even though I'm a lab instructor, I'm really trained as a theoretical physicist. But they really had to isolate their apparatus. Absolutely. And I don't know the technical details of how they did it. And, you know, I was only half joking. I think at one point I mentioned cars driving in the car park. That literally shows up in the apparatus. So I don't know how they get that isolation. I don't know.
Okay, thanks.
No worries. Thanks, Andy. Thanks.
We need to find an engineer to come and give us a talk about the specifics of the actual instruments, don't we? That'd be very interesting.
I just thought it was a set of really, really tight bolts that stopped it stretching, but
I was going to say, imagine the collimation on that.
Excellent.
Before you go on, I forget who it was, but someone asked about the time scale of the event. So I just pull up one of my books, and you know the event lasted half a second or so.
Okay.
Gosh, okay.
Pretty quick.
The first event that they detected, so I write on the order of a second. So it lasted half a second or so.
So I mean, the diagram that, because it was my question, the diagram that you had these two things orbiting each other.
Yes.
Does each wave correspond to one revolution or what?
Several revolutions. They really spin fast when they get close, or orbit quickly, not spin fast. But that would be several revolutions. The last few revolutions.
Okay, so it's not a constant. It's not a constant thing that's being produced. It's only when they actually get in really, really close that they start to produce the waves. Is that right? Have I understood that right?
Yes and no. They are constantly being produced, but they are not being constantly produced with sufficient amplitude to be detected.
Okay, I understand.
It's only when they get close to each other that the amplitude goes up and we can now detect them.
Got you. Understood. Thank you for clarifying that. John Foster, you want to click whichever button it is, unmute yourself, sir.
Oh, he's got background noise.
Too much noise. Okay, not to worry. So John says they isolate, but wouldn't it be the case that they need to frequently remeasure the dimensions extremely accurately? I presume, John, that's the arms of the detector that you're referring to there.
Yeah.
Yeah.
And they're constantly monitoring this. They have a signal, and they have a signal that they're constantly monitoring to figure out what's going on. They never have a baseline signal. They're constantly sending light through the interferometer.
Okay. Yeah. Understood. Okay. Well, that's all the questions that are coming from the chat. Unless anybody's got anything else.
That was great. Thank you,
That
George.
was, yeah, that was, yeah, really, really interesting.
Well, thanks for having me. I enjoyed this tremendously.
Oh, it was a pleasure. Thank you.
Absolute pleasure. Yes, indeed. Yes, indeed.
I-
Yeah,
I-
so
I was just
go on,
gonna
Grant,
say,
sorry.
I'm getting distracted by Andrew Smith, who looks like a Bond villain at the moment. I don't know if anyone else can see this. He's got a cat. Just he literally looks like a Bond villain.
And like you say, George, obviously, you know, these experiments don't stand still. The technology moves on, and you know, it's obviously clearly really interesting to see what happens as time goes on, and see what else we are going to be able to measure. But wahahaha. So George, thank you very much indeed. As we were talking earlier, it's not too bad a time for George. It must be about lunchtime for you now, I think.
Yeah, it's gone half 12.
Excellent. So I think you deserve a cup of coffee or whatever it may be.
Tea. I don't drink coffee.
Tea. Excellent. Oh yes, good man. Good man. Well done. Well done. Yeah, tea indeed. Right. So thank you very much indeed, George. Really interesting. And again, that when we get it uploaded, that will be available for you to sit back through at your leisure. Grant, have we got a speaker booked for next week?
We have. I'm a bit more organised than I was last week. So we've got Mike Frost is joining us next week, and he's going to be giving his talk on the green flash, which
okay.
I've seen this talk before. It's really interesting. I don't know if anybody, I'm sure some of you will know about the green flash, but it's a phenomena when the sun is setting. Just before it totally sets, you get a little green flash. It's very hard to kind of track down and be in the right place at the right time. But it's a very interesting talk. So hopefully you guys will enjoy that one.
I think we need a proper SGL trip at some point to go to somewhere hot and very warm and see if we can spot these. Right, okay then, guys. In that case, then everybody stay safe, and we will see you all next week for that talk. Thanks very much indeed,
Thanks
George.
all.
Thank you,
Thanks,
sir.
George. Night, Daz. Thank you all. Bye.
Night all.
Bye.